Okay, let's go. So you have some new levels. I'm not going to add a homework to Bolzano-Weierstrass. You're studying, but let's prove Bolzano-Weierstrass so we have it, and we'll go back and finish the proof of monotone subsequences. Okay, I want to make sure I cover this. So Bolzano-Weierstrass, this is the big reveal. It says if your sequence is bounded, at least our version of Bolzano-Weierstrass, all you know about the sequence is that it's bounded. We want to show that there's some subsequence so that A composed with that subsequence is Cauchy. Okay, let's talk about it in natural language. So our theorem, which is some version of Bolzano-Weierstrass, says we have a sequence A from the natural numbers to, the rationals or the reals. And we know, let's call this HA. Is it called HA? Yeah, of course it's called HA. What else would it be called? We know that the sequence is bounded. Okay, and our goal, what's our goal? So the fact that the sequence is bounded, all that tells us there's going to be some M positive so that A, whatever it's doing, it's bouncing around, but it's bouncing around within M to minus M. Okay, what's our goal? There exists a subsequence, exactly. There exists a sigma. Question. There's sequence bounded by, which was just an upper bound, and sequence bounded is in absolute value. Yeah, we can check our definition. There's sequence bounded by, which is just an upper bound without absolute values, and sequence bounded. It's not great nomenclature. I'm just making this up as I go, and I'm not being consistent, but sequence bounded is really bounded, above and below. In other words, in absolute value. In fact, one of the theorems, we have this abs LT theorem. We're going to need an abs LE less than or equal to theorem that does the same thing for that. Okay.
Question, the second one, the homework, was asking, like, is there a sequence that is monotone, that is not monotone, and is Cauchy? Was that intentionally just monotone increasing, or was that because the monotone A is just an increasing? So it didn't, like, the question didn't include that it has to not be antitone either.
You're talking about problem set 12? Problem 2?
Like,
let's see, did I not state it well? There's
an antitone bound, so like
yes, of course, I want it to be not monotone and not antitone. So if you solved it that way, that's perfectly fine. That's on me for stating it imprecisely. But
I solved it that way, and I wrote a note. I'm like, I'm pretty sure following the phrase wrong.
Right.
Okay.
Yeah. Does there exist a sequence of real numbers that's Cauchy, but not monotone nor antitone, is what I should have said. Thank you. Yeah.
So is in this problem just a proposition or not proposition? So this or was the idea to make us solve on it?
You must begin this solution with either left or right. Yeah. So as stated, currently, I'm working on changing the game server so that at some points like this, it will only allow one of two tactics as its next step. Right now, yes, you could solve this trivially because it's trivially true, but I want to change it so that I can force you to prove one or the other. What was the, this is problem level, it's this P set 12, level 2, not monotone and not antitone. Thank you. You get a +1. Yeah.
Wait, even if you make it not monotone, can you just still use 1 over n and lean, because the dummy variable, like the dummy value for n equals 0 is 0, so it's still not antitone or monotone.
That actually genius.
That is genius. Of course, what I want you to say is -1 to the n over n.
Yeah, but this
So that
is so hard to work with.
I know, it's good practice for how to work with it in Leany. You're absolutely right. Okay, so I have to think about this. So 1 over n is works. Yeah,
You have to figure this, like,
you're absolutely right.
how would you exclude?
+1 for Joe. You can, but there is such a thing. It's called the positive natural numbers. And it's a horrible, if you think working with reals and naturals is bad, don't even look at positive naturals.
Is there some way to do like, I guess it doesn't really matter, but is there like an easy way to do a piecewise function?
Yes,
'Cause,
we're
like,
about to see
I
that
was
right now.
thinking, like, cause my first thought was just like intentionally force it to be like A0 equals 0, A1 equals 1, A2 equals -1, and then everything else is 0.
Oh, wait, there's a good point.
You
That-
can definitely
and I
do
tried
that.
To see if I can.
You can definitely do that. Joe points out that lean is already built in that way. 1 over n is not a monotonic sequence, nor is it an antitonic sequence, because of the way division is handled. I need to do, okay, so this was an experiment. The experiment failed, and I have to do a better version of this problem for the future, but it's too late now. More questions? Let's go. Bolzano-Weierstrass. So we have this abs LE is a new theorem, which is like abs LT. You proved in the problem set, is Cauchy of antitonin bounded? Yes. If it's bounded from below and it's antitone, then it's Cauchy, just like we proved, but we didn't finish the proof, so we'll come back to it. And then this antitone subsequence of unbounded peaks is the last thing that we are going to prove. This is the antitone version of what we're going to prove, okay? So given those things, we want to conclude from the sequence being bounded that there's a subsequence which is Cauchy. All right, let's work on that. So our goal is there exists a sigma, subsequence sigma, and is Cauchy A composed with sigma. Okay, how are we going to do this? Joe. Yes? Exactly. By cases H, which is unbounded peaks, A. Okay. Maybe we first, before we break it into cases, because we don't want to do the same thing, we don't want to repeat things. So maybe we should pull out this M. Let's see, let's choose M pos HM using HA. In fact, maybe it's better to call this HA using HA. That's perfectly fine too. HA is going to get destroyed. What that will give us is M, real or rational number. It'll give us M pos, which is the fact that M is positive, and it'll give us, we can still call it HA, we can call it HM, which is that for all n, absolute value of AN, is it strictly less than or less than or equal to? Does anybody remember? I think it's less than or equal to. Less than or equal to that. Okay. And now, can I rewrite by, let me just have a new HA. Okay, let's have a H upper. H up is that for all n, absolute, not absolute, but AN itself is less than or equal to M. This is going to be a little annoying. By intro n, and then what? Maybe bound. Maybe I have to do bound together with a call to HA of n. Maybe not. Maybe bound will do it. Should we try it? All right. Let's go into this just a little bit to see what will work. Choose M pos, and HA using HA. Okay. So we have our M. We have this. Let's have H up, upper bound, which is that for all n, AN is less than or equal to M. And let's try intro n bound. This is so frustrating. Okay, so the reason bound doesn't see it is it doesn't see abs LE. So let's just try this again. Bound. Okay, intro N. So we've introed N. Let's specialize HA. Specialize HA to N. Then apply, or rewrite actually. Rewrite by abs LE at HA. And now we should be able to do bound. Do you understand what I'm seeing in my head as I do this? So the intro N is, because it starts with a for all N, now we have a little n. We're going to specialize HA to that little n, but not globally, just locally, just inside this half. So now we have that the absolute value of AN is less than equal to M. Now, when I rewrite by this theorem, abs LE says the absolute value is less than or equal to, if and only if, you have this lower bound and this upper bound. And then I think bound can see through the 0.1 and 0.2. Or actually, it's not even bound. It's then apply HA.2. Are you seeing that in your mind? Let's see if this works. Amazing.
How do you know it's not true?
Yeah, because if you look at the statement abs LE, so this is a theorem. What happened here? Uh-oh. Okay, that's weird. That's some kind of bug. I have to figure out what happened there. If you look at abs LE, it's abs LE if and only if, and there's the minus B lower bound is the dot 1, and the upper bound is the dot 2. Okay. And similarly, let's grab a H upper bound and H lower bound, low, up and low, I guess, whatever, which is that minus M is less than or equal to AN. For the same reason, intro N, specialize AHN, rewrite this, apply HA.2. There's got to be a better way to do this. I don't want to think of a better way to do this. We've got our upper bound and our lower bound before we split into cases. And I think that's basically everything we can do. I think that's everything we can do before we split into cases. Okay, so we have H up, we have H upper bound, H lower bound, up, down, I don't know. For all N, negative M is less than or equal to AN. Great. Now we're going to split it into do you or do you not have bounded peaks? Let me postpone the case. Well, it's annoying if I say it's not true that we have unbounded peaks. All right, let's just go into it. If you have unbounded peaks, then there's a theorem which is called antitone subsequence of unbounded peaks, which is what you'll prove in problem set 13, which for some reason got sent to anonymous. I know where that happened. Okay. All right. So it's the analog of the thing that we proved elsewhere. It says if your sequence has unboundedly many peaks, so it keeps having these peaks. You remember what peaks are. This is a peak if there's no future value that goes above that, and then maybe there's another peak and there's another peak. So this is a peak, that's a peak, that's a peak. Okay. So let me just say have, and I'll figure out what it is, and it's going to be this antitone subsequence of unbounded peaks, anti of unbounded peaks. I'm just doing a shorthand. All I have to feed into that is A, the sequence, A, and the fact that the sequence has unbounded peaks. So that's called H. Okay, everybody see that? So this is going to be by apply this. What do we get out of that? We have what should we call this? In fact, we don't even need to have a have. We don't need to have it. We can choose it. Because what this will give us a sigma, the fact that it's a subsequence, and the antitone. Okay, so choose sigma, the fact that it's a subsequence, sub sigma, and the fact that it's antitone, anti, using this. Everybody see that? Everybody see how I work my way towards that? Okay, so we're going to choose sigma, sub, and anti using that. And now what? Okay, fine. Use sigma. Yeah. Use sigma. Use sigma. So now the goal will be that it's a subsequence and that it's Cauchy. So split ands. Let's split the two ands up. Split ands. The first and will be the subsequence. That's sub, yeah, so apply sub sigma and we're done. And now the last thing we have to show is Cauchy. That's not what we know. We don't know is Cauchy. What we know is antitone. So it's antitone, and we want to show that it's Cauchy. What's the last thing that we need for that? Exactly. Is Cauchy of antitone bounded? Right. That's the theorem. Is Cauchy of antitone bounded? Which says, so again, let's think about what that says. I'll just put it over here. Is Cauchy of antitone bounded? What does that take? It takes a sequence. The sequence is A. It takes a number m so that m is a lower bound. What's that? Very good. Very good. So it's not A. It's not actually A. It's A composed with sigma. That's our sequence that's going to be Cauchy. That's the sequence we're trying to prove is Cauchy. Thank you. Which value of m do we want? Minus m is our lower bound. Minus m. So this is minus m. Then we want this fact hm, that this is always a lower bound. H low. That's our H low. H low is exactly what we needed for that. H low. Okay. And then the fact that A composed with sigma is antitone. Anti. We call that anti. Very good. Will H low work directly? No, it will not. No, it will not. So we have to prove this first. So let's that's exactly what we want. We want to have H low prime, which says for all n, A of, I guess I should put the minus m first. Minus m is less than A composed with sigma of n. Okay. Let's see. If I just do by intro n bound, there's a chance bound will work, but if not, then actually bound won't work because it has trouble seeing through this. So I intro n, maybe I have to change the goal to negative m is less than or equal to A of sigma of n. And then bound should work. Then bound should see, well, it's at that point, it's just apply H low to, instead of n, to sigma of n. And then we're done. Daniel. So rewrite is good when you have a theorem about what sigma is. The fact that this thing, I mean, the fact that A composed with sigma is equal to A of sigma is just definitional equality. So it's not a rewrite, it's actually a REFL. And what change is doing is secretly is it's setting up this thing is equal to that thing by REFL. Does that make sense? Again, if your proof on a handwritten thing, I'm trying to teach you how to play the game, but if your handwritten proof, says something here which isn't, which doesn't actually work, it's okay as long as, this is why I insist on not having naked applications of tactics. You tell me what you're trying to show, and I say, yeah, of course that should be true. Maybe you didn't get the right letters to make it true, but it should be possible. Okay, so then we have this H low prime. That's exactly what we have to stick in here, an anti, and then this is exactly what we want. This will conclude is Cauchy of A composed with sigma, which is what we're trying to do. So then apply. All right, so that finishes this case. Does that make sense? Our other case, so now H says it's not true that we have unbounded peaks at A. So now what? What's that?
Push that.
We don't want to push, that's a good guess. we have another theorem, which is the one that we were starting to prove but didn't finish last time, which is monotone of bounded peaks. If it's not true that the peaks are unbounded, we call that monotone of bounded peaks. Let's have a glance at that theorem, remind ourselves what it says. Monotone subsequence of bounded peaks. Great. Monotone subsequence of bounded peaks says if you have a sequence and it's not true that it has unbounded peaks, then the same thing. Okay, so monotone subsequence or whatever of bounded peaks where we feed it A, then we feed it H is exactly the thing that we want, then what we will conclude is there exists a sigma. So we can go straight to choosing it. Choose sigma, subsequence sigma, and then mono using all of this. That gives us a sigma. That gives us the fact that it's, so now we can use that sigma, split ands as before. Why is the subsequence a subsequence? Apply sub sigma. And now let's think about, let's just copy this, have H up prime, which is that for all n, A composed with sigma of n is less than or equal to m. And it's the same thing. I won't write it out here. We're just going to copy that. And then we're done. Apply is Cauchy of mono bounded, whatever that's called. We have to give it A composed with sigma, bless you. The bound is M. The fact that it's upper bounded is H up prime. And then the monotonicity is mono. And that's the proof, okay? So the proof is very, very simple. The reason Bolzano-Weierstrass is true is because if you're bounded, then either you have an increasing subsequence, or if not, you have a decreasing subsequence, depending on whether you have unbounded peaks or not. Now you have an unbounded subsequence. Now you have a bounded increasing subsequence, therefore it's Cauchy, or you have a antitone subsequence, which is also bounded, and therefore Cauchy. Does that make sense? So it's really the Bolzano-Weierstrass, it looks like a fancy theorem, but it's not. It's a combination of two other things. It's a very simple combination of two other things that are profound. The profound things are, if you're increasing in bounded, then you're Cauchy, or the other way around. The other one is whether you have unbounded peaks or not. If you have unbounded peaks, then there's a decreasing subsequence. And if not, then you have an increasing subsequence. That's the last thing we have to show. Does that make sense? Let's prove it. Let's put it into the machine. All right, reload. Bolzano-Weierstrass. Major theorem in mathematics. And, oh yeah, okay. So here we are. We did these first steps together. Let's do the by cases. So I'll go right to here. By cases, H, unbounded peaks, A. Boom. We have two goals, an active goal and a later goal. And we have that it's unbounded. Okay, so choose sigma, subsequent sigma, and anti using, oh God, what is this called? Antitone, yeah, this one. Can I just copy that? Paste it into here? There we go. That's all I wanted. I think this will still keep working, even though it's red. I just didn't want to remember what this was, how to write this. I just need to feed this A and H. Let's try this. Beautiful. Okay, we've got our sequence sigma. We know that it's a subsequence, and we know that A composed with sigma is decreasing. Okay, use sigma, split ands. That's all good. Why is it a subsequence? Because it already is. Apply sub sigma. Done. You see, at this moment, we have three active goals. I mean, three goals total, because we've been breaking goals into sub goals and so on. Now we have a second goal. Why is it Cauchy? Okay, So here's where we have to have H low prime, which says that for all n, what? Negative m is less than or equal to A composed with sigma of n. And why is that true? Give me the n. Let's change. I think the change is necessary. We could experiment with it. Change the goal to that. And once we do that, we should just be able to apply H low to sigma of n. Does that look right? By the way, notice that this no longer scrolls horizontally. So someone saw the video and PR'd a change that makes it dynamically get larger, which is so cool. And now we can see the whole thing even as we're writing it. So we have this H low prime, and that is exactly what we need to get the last theorem to go. So it's apply is Cauchy. Oh God, I'm gonna have to grab it because I don't know how to write it correctly. Is Cauchy of, here it is, of antitone bounded. So I'll just grab that, paste it there, and then we can go back to our view. Is Cauchy of antitone bounded with what sequence? It's not A, as Daniel pointed out, it's A composed with sigma. This is exactly the kind of thing that is so easy to gloss over in natural language, and it's like, oh yeah, it's just, no, which one? Which sequence? Why? What is the bound? It's not M, it's negative M. Why is that a lower bound? That's H low prime. And I called it anti. Anti is the antitone property of A composed with sigma. And that's it. The intermediate goal is solved. You're seeing everything in your mind as we do this? Okay, and then we do the same thing on the other side. Okay, so choose sigma, sub sigma, and mono using, oh God, I'll just copy and paste it. Is it okay when I do this, or does it really confuse you guys when I jump around like this? Mono subsec of bounded peaks, that's the one that I want. Monotone subsec of bounded peaks. There we go. That's what it's called. That's how you write it. What do I have to give it? I have to give it A and H. H already says exactly what we need it to say. You see that? H says it's not true that we have unbounded peaks. Boom. Beautiful. We have our sigma. We have that sigma is a subsequence, and we have that A composed with sigma is monotone. That's our increasing subsequence along A. So use sigma, split ands. Nope, that's not how you spell ands. There we go. Why is it a subsequence? Apply sub sigma. And why is it monotone? Okay, so there's this is Cauchy of monotone bounded. Whatever it's called, is Cauchy of monotone bounded, which I think is the theorem we have yet to. So I'm going to apply is Cauchy of monotone bounded. Let's slide this over. Okay, what do I have to feed into it? A composed sigma. I have to feed into it M. I have to feed H. Oh, did I not do H upper bound? Darn. What's that? Say it again. Oh, try proving it in this line. Very good. Okay, let's prove it in the line. So it's going to be intro by intro n, then what? Change A sigma n is less than or equal to M. Then what? Apply H upper of sigma n. That should work. You see what we're doing? What it wants is a proof that for all n, what it wants here is a proof that for all n we have this upper bound. And instead of making a separate half about it, we can just do it. Give me the n. We know that it has trouble seeing the composition, so A of sigma of n. And then that's exactly what H up does at sigma of n. Great. And then we did that, and now we just need to say mono. That is Bolzano-Weierstrass. Okay, that's a big theorem. Now, there's a gap in our theorem. There's a couple of gaps in our theorem. The main gap is, well, that it crashed. No, that's not the gap. The main gap is that we didn't finish the proof of if you don't have unbounded subsequences, then you're monotone. The antitone subsequence of unbounded peaks is actually an easier theorem, so I'm leaving that one for homework. but it's a little bit technical. It's quite a bit technical, which is why I want to do it together to prove this monotone subsequence. So let's do that real quick, and then we'll just review the rest of the time. Okay, make sense? Is everybody happy? Does everybody understand not just how to do it in lean, but what the math means? If you're bounded, then there's either an increasing or a decreasing subsequence. In either case, you get an increasing bounded sequence or a decreasing bounded from below sequence. In either case, you get Cauchy. And once we know that Cauchy implies limit, that's the last thing we have to do. Then you get what is the Bolzano-Weierstrass theorem in textbooks, which says if you're bounded, then there's a subsequence that has a limit. Okay, great. Let's go to why is it true that when you have a monotones, that when it's not true that unbounded peaks holds, then you have a monotone subsequence. Okay, so we started the proof of this last time, but we went through it quite quickly, so let's just start it again. Any questions? Everybody's following along. Okay, so here's our theorem. This is called what? Monotone subsequence of bounded peaks. I guess a better name for bounded peaks would be unbounded peaks, or not unbounded peaks or something, because that's technically what we have. But we're not gonna, it's bad, the name is bad enough as is. Let's not make it worse. Okay. What are our stuff? So our objects, we have A, which is a map from the naturals to the rationals or whatever. We have the hypothesis on A that it's not true that unbounded peaks holds. Unbounded peaks A holds. And our goal is there exists a subsequence, there exists a sigma, which is a subsequence, and the monotone of A composed of sigma. All right, now I don't need this. We can zero in. All right, first of all, let us remember what it means to be unbounded peaks. So let's start by changing at HA. Maybe this is a good, yeah, this is a good quiz. This is a good quiz. Let's change at HA to something that doesn't involve unbounded peaks or is a peak. Think in your mind what it should mean to be is a peak, and then think in your mind what it should be for the set of peaks to be unbounded. So I wanted to say it's not true that something, and let's work out what that line is. Take like 1 minute to think about what that line is. Don't use is a peak and don't use unbounded peaks. I wanted to go down to the core axioms, the core objects. In other words, recall is a peak AN means what, and unbounded peaks A means what. So fill these two things in and it'll be very easy to fill this in. Take 30 seconds. If you had to invent this theory from scratch yourself, how would you do it? I already gave the hint that peaks is an important concept. What is it? Shouldn't take you very long at all. Just think about it. Draw a picture. You draw a picture for what a peak should mean. You should very quickly be able to come up with what that definition is. And then what does the word unbounded peaks suggest that we say?
Honestly, don't know if it's strict inequality or.
Yeah, very good. I don't remember myself whether it's a strict inequality or not. It doesn't matter. That's not what I'm concerned with. Okay, we got it? Good enough? Let's hand them in to Joe, please. What's that?
What's the date today?
It doesn't matter. I don't know. Anybody know? 24th. Thank you. Yeah, October's flying. You. Okay. You. Any more? You. 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 Is that everybody? All right. So. Is that everybody? Got one more? You're gonna give me a little tiny script? Can I buy you some paper?
Why does it have to be a, you know, like,
All right.
Yeah. All right. There's like reams and reams of printer paper. Just grab some paper. Oh, one more. Thanks. All right. Again, the quizzes don't matter. Well, the quizzes are an opportunity for you to test your understanding, right? Is a peak. What would it mean for is a peak? Here's some sequence. We have a peak at n if what? Hyman. Exactly. The future values are all not exceeding this. So for all m greater than or equal to n, I forget if this is greater than or equal to or strictly greater than, whatever, am, this is n, the value at m, the later value, am, is less than or equal to an. Okay, if all future values are below. This one has to be less than or equal to. Peak does not assume that you're strictly decreasing. We never said we're going to be strictly decreasing. Okay, but that's what it means to be a peak. You can look down, you can look out, and you never have to look up to the next value. How about unbounded peaks? Go ahead, Akil. Yep.
There exists a lowercase n greater than, I don't know if it's.
Yep, me neither. Good.
That is the peak.
Beautiful. Okay, so unbounded peaks means no matter how far out you go, you still find another peak. There's a peak, and there's a peak, over here's a peak, and over there's a peak. Okay, that's telling us we have a decreasing subsequence. Question? Do you have?
Maybe I don't understand it, but I said for all n, not is a peak a.
That is wrong. That is wrong. And that's going to be part of what makes this so difficult. This is going to be, I think, one of the more difficult things that we do technically. And the reason it's there could be, what you're saying is there are no peaks at all. Which is not the same as there could be some number of peaks, but at some point, after some point, there's no more peaks.
But if there's a peak,
Yeah, let's draw the counterexample that you're worried about. So here's a peak, here's another peak, and then from this point on, we're increasing, but we never get back to here. It is, no, that's not unbounded peaks. Sorry, you were asking about,
no,
you said your version of unbounded peaks was what? Let me write it down.
all not is a peak A.
It's not true that is a peak AN. But this is a peak. And this is a peak.
But
This says there is never a peak. What's that? Not necessarily, because, you know, this number is not a peak because I get above that, and this number is not a peak because I get above that, but I'm not monotone. Right? So this says nobody's a peak. That's not the same thing as, you know, I have some number of peaks, and then after that. So, sorry. I'm talking about the I'm jumping ahead to the negation of this. What unbounded peaks literally says is for any n, no matter how high it is, there's always some point. So no matter where capital N is, after this capital N, I'll find some other value, little n, so that this value is a peak. And what you're proposing, your unbounded peaks prime, is that it's never true. For all n, it's not true that is a peak an, which we want unbounded. We want there to be not just do we want there to be no peaks. We want there to be infinitely many peaks. No matter how far out you go, you'll still find more peaks.
Yeah.
I think you were thinking about the negation of unbounded peaks, and this would still be wrong. Yeah. So the case we actually care about is right here. So let's write it out. For all capital N, there exists little n. I don't know if it's greater than or equal to, so that is a peak. And what does is a peak say? It says for all m greater than, maybe strictly greater than, am is less than or equal to an. Okay, so that's the theorem whose negation we're assuming. That's the hypothesis whose negation we're assuming. It's not the case that no matter how far out you go, there's a value after that capital N, so that for all values little m after that, you never go above the value at n. It's not true that there are infinitely many peaks. Does that make sense? Hopefully seeing the symbols is actually more clear than me talking. Okay, Brandon, question?
Like, I'm just, so there are, what, different like capital N, little n.
Yes.
There's only, there'll be three.
There are three inequalities. One of them is guaranteed. This one's correct. These two we have to double check. So let's double check them. So definition, what did we say when we defined is a peak? Is a peak strict inequality? Good, we got that right. What did we say when we defined unbounded peaks? Also strict inequality. Okay, so we actually got them both right. And I think I even know why. You'll see in a second why I wanted those to be strict. Okay, that makes sense? Okay, so we're happy with the definition. And we've now changed HA to say this. And now what do we want to do with that negation? Push neg. Let's push that negation through. So push neg at HA. So now what does HA look like? Instead of a for all n, there exists an n. So that instead of there exists an n, for all n greater than n, there exists an m greater than n, so that this isn't true. A n is less than a m. Okay? Actually, I think what lean will do is will it negate it? I think it will negate it. I think it will negate it. Yeah, if we push negative, it'll negate. Okay, so let's just think about what that, let's draw a picture of that. So here's our sequence. There's some capital N, so that for all little n after that capital N, there's some other m that's strictly greater than n, so that am gets higher than an. Okay, so this says that an is not a peak. There may be, this is the picture I was trying to draw before. There may be some small number of peaks to start, but once we get going, there are no more peaks. Whatever is happening, we're always eventually going to get above the previous value. Infinitely often. Okay, this might be a peak. We might have some peaks early on. But after a certain point, no more peaks. Does that make sense? Does it make sense to you that that's what the words are saying? That this is what we assumed about HA? Okay. Now, here's where it gets interesting. What do we want to do next? Choose. Yeah, let's choose this capital N. Choose this capital N and HN using HA. Okay, so now we know where it starts. So what does HN say? I mean, this is kind of dumb. I'm just going to rewrite this again. HN says for all n greater than n, there exists an m greater than n, so that an is less than am. And we have that capital N. We're trying to pick out those terms. How do we pick out those terms? Remember what our goal is. Our goal is that A composed with some subsequence is going to be monotone. How are we going to create the subsequence? Ayman? Orbits, exactly, iteration. We're going to iterate things again and again and again. We're going to get it from an orbit. In order to iterate an orbit, what do we need to know about the sequence that we're iterating? It needs to stay above the line y equals x. Yeah, tau of n needs to be at least n. Okay, so if we get that, then we can iterate it. We'll get a subsequence, and we get the monotonicity. So we want to apply idea. Idea is we want to apply. What is that called? Theorem. Monotone. What's it called? Suck iterate? What's that? Probably, yeah. Suck iterate, I think, is the one. No, that just says that's if you iterate. No, it's here it is, subsequence of successor. Nope, that's not the one. Subseq of iterate. There we go. Subseq of iterate. Yeah. So we want let me write down subseq of iterate. Let's write it down over here. We want to apply subseq. I should instead of looking for the name, I should think like, what should it be called? Because that's what I would have called it. That's the point of calling things what they should be called. Subseq of iterate. If we have a function to iterate, so we have a function. Here I'm calling it sigma. I'm going to instead call it tau. So we have a function tau. We have the hypothesis on tau that tau of n is always at least n. That's that. And we have some base point n0. Doesn't matter what that is. Then subsequence. It's true that tau iterated n times from n0 is a subsequence. Okay? This implies that. We want to apply this theorem. So we want to get a value that's strictly greater than n and some base point and iterate it. Okay, but let's look at HN. HN says, this really says, what does it mean that for all n strictly greater than n? Well, this is the same thing as saying HN actually says for all natural numbers n, if n is greater than n, then there exists an m greater than n and an less than an. So what we would have done in the past is we would have said choose. This is our fancy version of choose, right? Given any little n, we'll get an m and we'll get this inequality, right? So let's choose tau. Tau will be our sequence that goes from n to m. So m will become tau of n, right? The fact that we have this bound, we can call tau bound. And the fact that we have this inequality, we can call what? Tau a tau? H a tau maybe? Because it says, this really says that a at n is less than a at tau of n. This is also now going to be tau of n. So maybe let's call that a tau. choose this using H capital N. Now, if we had another quiz, this is too hard for a quiz. What is the tau? So this gives us new objects and new hypotheses. Tau bound and HA tau. And what are these things? Tau is a map from N. So you give me little n. What do I give you back? Joe. Exactly. I don't give you back anything until you give me more things. Okay, that's why this is so technical. You give me a little n, you're not done giving me things. You have to give me a proof that little n is greater than capital N. So it's n to a proof that little n is greater than capital N, and I'm not going to give that proof a name. And then I'll give you a natural number. That's what tau is. I can't give you anything until you tell me that I'm past capital N. You have to give me two things. You have to give me little n, then a proof that little n is greater than capital N, and then I'll give you this the natural number m back. Okay? What's tau bound? That's a horrible bound. I could barely read it myself. Bound, BND. I don't know if that's any better. What's tau bound? It's supposed to be tau of n. It's supposed to say tau of n is at least n, right? For all n. But I can't write tau of n. Tau of n is not a natural number. Akil.
Like the input be that argument.
Exactly. So if you give me this hypothesis, then I can give you this answer. And maybe Lean won't name these things. Maybe Lean will leave it as underscores. So I'm not going to give a name to this. Okay, you give me a natural number, you give me a proof that that natural number exceeds capital N. I'll be able to plug those two things into tau, get a natural number, compare that natural number to the n that was originally there. Daniel.
Why is tau like n to this instead of just n?
Because P and Q, this is a little logic thing. P and Q implies R is logically the same thing as P implies Q implies R. We don't want to change it because the and you would have to like bracket n and then a proof that n is greater than or equal to h instead of just feeding it n and then the proof. It's actually nice. This is the nicer version. This is not taught in textbooks, but it in the future will be how everyone learns logic, just because it's actually a nicer way to do it, which you don't notice until you start formalizing. Okay, Jeff.
When you write P implies Q implies R, parentheses are Q implies R.
Yes. Yeah, you give me the P first, and when you give me P, I get Q implies R. If the parentheses were the other way around, you'd first have to give me P implies Q. And only then could I give you R. So the parentheses are like this. The implied parentheses are like that. Does that make sense? Okay, and what is HAT? I want to say AN is less than a tau of n. But as we know, I can't write tau of n. That's not a natural number until you prove that n is, so this is for all n. If n is at least n, big N, then you get this inequality. Should I just show you that is what's going to happen? Let's get this far into the proof, and then we'll keep going and figure out what the hell we're supposed to do about that. That's a major problem. We can't. What's the biggest problem with this tau? What do I want to use? I want to iterate this tau, right? I want to do it again and again and again. It's not a map from n to n. If I want to iterate this every single time I have to reprove this stupid theorem, it's going to be awful. So we have to do something else. But let me just at least show you that this is indeed what happens. Okay, so let's start from the beginning. The start of the proof is this change. So let's remember what unbounded peaks says. It's change not. It's not the case that for all capital N, there exists n strictly greater than capital N, so that for all m strictly greater than little n, am less than or equal to an at HA. Okay, great. It accepted the change. There it is. Let's push neg at HA. We push through. There exists. Beautiful. Let's choose NHN using HA. Now we have our HN, which is for all n, if n is greater than capital N. We're so used to there exists an n greater than capital N. No, this is a for all n, but not all n, only those for which exceed capital N. We have to allow for those initial peaks. After we get past those potential initial peaks, now the theorem kicks in and there are no more peaks after that. And so watch what happens when we put choose tau bound, and HA tau looks like hat. I didn't mean for that. Kind of funny. Okay. We have a tau. We need a proof that n is at least n, and then we'll get a natural number. Tau bound says, give me a natural number, give me a proof that it's at least n, I'll apply tau to n and that proof, and I'll give you a proof that it's greater than little n. And hat says, for any n, you give me this proof, I can compare a n to a of tau of n with that proof. Okay, so obviously we don't want to work with tau. So here's a suggestion. Forget these early values. The early values I want to just ignore and make up my own function, and hopefully we never have to deal with them. So the idea is, let tau prime be a function that really is from the natural numbers to the natural numbers. And it's defined like this. It's a function that takes little n and sends it to what? Well, if little n, and let's give this hypothesis a name so we can refer to it, if little n is greater than capital N, then return tau of little n together with a proof that it indeed is greater than capital N. Otherwise, I don't know, just something so that it's increasing. Remember what our conditions are for something that we want to iterate, is that it's increasing. So if I have little n, how do I want to make sure that it's above little n? N plus 1. Okay? Otherwise, n plus 1. Joe.
Map to tau and little n plus big N plus 1.
Yeah, so let me write that down. Your alternative proposal is let tau prime be what? The function that sends little n to?
Tau little n plus big N plus 1.
And now I need a proof by bound. Okay, you can do by bound. I wonder if it'll accept this or not. Let's try it. Let tau prime, which is a map from the naturals to the naturals, be the function that maps n to tau of n plus 1. And let's see if it accepts by bound. It does. Okay. And let's have a way to record what tau prime is. So have tau prime is, which is that for all n, tau prime of n is equal to what? I guess it's equal to tau of n plus 1 by bound. And that proof is REFL. Let's see if that works. So it's having trouble. And the reason it's having trouble is that this by bound, the fact that you're using a proof inside is causing trouble. I don't have a good explanation for this. This is above my pay grade in terms of what's happening under the hood in lean. Before REFL, let's see if that helps. Maybe. Oh, okay, very good. Very good. Let's keep going with this. Let's keep going with this. So we're gonna have the same issues as before. Now, let's prove a little theorem. We need to know that tau, in order to apply this lemma, we need to know that tau prime always exceeds little n. Brandon.
I think we need to like retry the other, because I think it's.
Oh, did it not,
Well, yeah.
reload? Thank you. Okay. Thanks a lot. Okay, hopefully that fixed it. Yeah, let's keep going with your alternate version. It accomplishes the same thing. I think that my first try was something like this, and then I ran into all kinds of issues, and so I abandoned it and went for this, and this works. And then I thought, oh, it's a good opportunity to show you how to do if then else. But let's go with your way. Okay, so we have this tau prime. In order to use this subsequence of iterate, I need to know, the main thing that I need to know is that tau prime of n is always at least n. So let's think about how we would prove that. So let's have a theorem that's called tau prime bound, which says for all n, tau prime of n is at least n. Okay. What's the proof? We have to intro n. Now, what do we have to do? Maybe rewrite. Let's rewrite by tau prime is. Isn't that what we called it? Tau prime is. So tau prime is, we'll replace tau prime by this thing. And now, can we apply, where is that tau bound? We want to use tau bound. Okay, so I'm going to write something like, I'm not going to write specialized just yet, but if we take tau bound, what value of little n are we sticking in? N plus capital N plus 1. And what's a proof that n plus capital N plus 1 is greater than n? By bound. By bound. So that will be a proof that tau of n and the inequality is greater than n. And I think that's exactly what we want. So just apply. You see that? So I think that will prove what we want. Should we try it? Does everybody see how we got this? Does this make sense? So let's try have tau prime bound is the fact that for all n, I should do it this way, n is less than tau prime n. And what's the proof? Gave me the n, rewrite what tau prime is, I guess at that n, although you don't need that n. And finally, apply tau bound itself, but not to n, but to n plus 1, together with the proof that that exceeds what we want. I think that's going to do it. Failed. And unfortunately, we can't see where it failed because it's a one-liner. Reload. Okay, so it got to here. So we can see. Okay, that's good. So we want to know that n is less than tau of n, and why is tau bound not proving that? It is proving that. No, but it should be able to. Really? It's this question mark M115. Yeah, this is the kind of thing where I think it's this by bound, which is screwing everything up. Okay, we tried. If you don't mind, we'll abandon this direction and go back to the original idea that I know does work. Instead of bound? And what do you want to feed into it? Nothing. It shouldn't require It shouldn't require anything.
It makes sense though, because if it worked before, it should be working now.
I mean,
Why don't you specialize instead of applying?
okay, let's try specialize. Let's see what it does. Specialize. Yeah, it won't specialize. Ah, it will specialize. And now bound. Okay, so it wouldn't do it in one fell swoop, but it did it in two fell swoops. Okay, this is the kind of stuff I don't like because we shouldn't have to deal with experimental experiments like this. But all right, so if we specialize this, by bound probably would have worked. And then bound won't do one more bound. Then we get our tau bound. All right, should we try this? Let me just see if the linearith really was the thing. I think by bound will work just as well. Yeah. And let's just check that that gets no error messages, no error messages. Okay, I don't know why. We're in some uncharted territory here. So we have our tau. We have the fact that tau is bounded by A. That means tau of n is bounded by n, down below by n. That means we can apply, what's our theorem? Subsequence of iterate. Okay, so let's just build it up. Subseq of iterate. It takes a function tau. What's our function tau? Tau prime, because that's a function from the naturals to the naturals. It takes a proof that tau prime is always at least n. That's called tau prime bound. And then it takes a base point. Where should we start? How about starting at n plus 1? Let's just get beyond that capital N. So let's start at n plus 1. Once we're past n plus 1, all of this should work out. Okay, so so if I do by apply of this, what should we get? We should, why don't we define, before we try to apply this thing, I don't know. Do you want to define a sigma that does it? Instead of needing to refer to that sigma? Sigma should now just be iterates of tau. So I'll go over here and I'll say let sigma, which will be a function from n to n, colon equal the function that maps n to tau prime iterated. I don't think we needed n plus 1 times. We don't need it n plus 1 times because it's always going to be strictly increasing. Yeah, of n plus 1. Okay, and then so let's write this down. Let sigma be a function from the naturals to the naturals, which sends n to tau prime to the n at n plus 1. Does that look right to you? I think that's going to be okay. Let's record what sigma is. So have sigma is, for all n, sigma n is equal to tau prime iterated n times of n plus 1. And that's by intro n and REFL. Okay, so now we know what sigma is. And now I think we can say have let's call this sub sigma, which is the fact that subsequence sigma, isn't that, what's this theorem? It gives us subsequence of tau to the n. So this is going to be subsequence sigma. And what's the proof? It's applying subseq of iterate to tau prime together with this proof tau prime bound and together with the base point n plus 1. You guys following? We got it. Okay, so let's use sigma. Whoops, really? Use sigma. Okay, do I have two uses now? Am I gonna have a problem over here? Let's reload. Da, 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 da. No problem. Use sigma, great. And then split ands, split ands. And then why is it a subsequence? Apply sub sigma. We already proved that it's a subsequence. Beautiful. All right, why is it monotone? Why is it monotone? How do we prove monotonicity? Monotonicity is about for all I and for all j, but there's a simpler way to do it. We can go just from I to I plus 1. What was that theorem called? That theorem had a name. It was monotone of successor. Okay, so let's apply monotone of successor. And now it's enough to do it one step at a time. So let's intro little n. Okay, let's change so that it looks nice. A of, what is sigma? Sigma is tau prime to the n of n plus 1. That is going to need parentheses. Is less than or equal to A of tau prime of n plus 1, whoops, to the n plus 1 of what? N plus 1. Is that right? That look right to you guys? What we want to prove is A, which is A of sigma, and is bounded below by A of that. So I think that's good. Good. Now, tau to the n plus 1, we want to turn, what's the point? How are we going to get the monotonicity? Yes.
It's like subsequence variable.
Exactly. We need this tau hat, first of all. Okay. By the way, maybe we should prove that tau to the n of n plus 1 is always greater than n. Let's just prove that. Have h tau prime, maybe is for all n. We're going to need this fact. Tau prime of n, tau prime to the n of capital N plus 1 is strictly greater than n. Right? We're going to need this fact. This is what I get for going off script. All right, we can do this. We can do this. So why is this true? Maybe I shouldn't. We have a little n? Yeah, we have a little n. Let's do a dummy variable, k, just so we don't get confused between our dummy variable and that. So let's intro k. Now what? How are we going to prove this inequality? How about induction on k? Induction prime. In fact, we'll be able to see if we go into this mode. Okay, so, oh, we lost it. Okay, have tau prime, h tau prime, which says for all k, big N is a lower bound for tau prime to the k of n plus 1. So I intro k. Okay, we've intro to k. Why is this inequality true? Let's do induction. Induction prime k with khk. Why is it true when tau equals 0? Yeah, or norm num or something. Let's try norm num. Does norm num do it? It does. Norm num does it. Now, we know that this lower bound holds before, and why does it hold after? So if we specialize, God, I'm going to run out of time again. We can do it. We can do it. If we specialize tau prime bound, then we know that tau prime is at least, okay, so specialize type tau prime, specialize tau prime bound to what value? To the value, yes, tau to the k of n plus 1. Tau to the k of n plus 1. Does that work? This is lower bounded by that. That's lower bounded by that. And now it's linearith between these two things, or just bound. I think bound will do it. Beautiful. No? What's wrong? No. Okay, fine. So then just linearith instead of bound. Linearith. What do I have to feed linearith? Linearith isn't going to do it by itself. I have to feed it HK, and I have to get it tau prime bound. We're not done. We're not done because this tau and tau prime need to be put together to make a tau of k plus 1. So we're not yet at linearith. We're not yet at linearith. We have to rewrite, show tau prime of tau prime to the k of n plus 1 equals. Come on. Come on. I'm really testing this system. Tau prime to the k plus 1. Slow. Go slow to go fast. And why is that true? By apply suck iterate. That's not where I want to do it. I want to do that at tau prime bound. At tau prime bound. And now linearith. Okay, we got through it. We got through it. We know that this inequality always holds. And so now we're almost done because what we have to do is stick in God, I'm out of time. You see what you have to do? There's only a few steps left. I want to use tau prime. The tau prime bound isn't, I want to use hat. We still haven't used hat. You see? So right now we've proved the thing that we need to put into hat. So let's specialize hat. Specialize HA tau to tau to the n, tau prime to the n, we're almost there, of n plus 1. Okay, and then why is that bound? That lower bound is what we just proved, h tau prime. So h tau prime. No, no, you won't take h tau prime. What do you want? H tau prime says tau prime, tau to the oh, it's h tau prime of what? Of little n. H tau prime of little n. H tau prime of little n. Beautiful. We're almost there. Okay. Boom is less than that. And now I just have to rewrite one of these rewrite show tau prime of tau prime to the n of n plus 1. This is going to work, and then we're all going to go home. N plus 1 of n plus 1 by apply suck iterate. And I need to do that rewrite at what? At hat. HA tau. Thank you. Still no? What's the error? Oh, there's a tau here and a tau prime there. I give up. I give up. Okay. My ways. Anyway, we're out of time. We're almost there. You see what you have to do. You see why this is the hard one that I wanted to do together.